So, you finally settled in on the couch, right? You press the power button on your remote, and absolutely nothing happens. Man, is it frustrating? But, what's actually going on inside that dark piece of glass? It isn't just a random glitch. It's actually a microscopic, high-stakes whodunit happening right inside your dead television. Today in this explainer, we're going to crack the case on LCD TV mainboard breakdowns. We'll be exploring the invisible engineering gymnastics required literally just to turn a screen on. Okay, so here's our roadmap to hunt down the culprits today. We'll kick things off with the power struggle, then move on to LDO regulators, investigate buck converters, understand the freewheeling defense, and finally decode DDR termination. All right, section 1, the power struggle and the voltage hurdle. Now, to understand why a TV fails, we really first have to understand the massive balancing act happening between raw processing speed and these super delicate voltage limits. Let's start wide to establish our geography here. If you look at a standard LCD mainboard, honestly, it kind of looks like an aerial view of a sprawling green city. And every single block, line, and pad has a distinct purpose in bringing your television to life. It's basically this highly coordinated metropolis of electricity. Zooming in just a bit reveals a pretty dizzying array of components mapped out all across this landscape. You've got the core processor, the flash memory, the audio power amp, and all sorts of various multiplexers. It really shows you just how complex this environment truly is. There are basically distinct neighborhoods handling audio, video, and memory. But hey, we aren't going to look at the whole city today. We are looking for very specific suspects behind our television's demise. So, directing our absolute focus to the top left of the board, we find the power supply section. And this is exactly where our 3 microscopic suspects reside. When a TV board defaults into a systematic shutdown, the root of the problem is almost always hiding right here in this one specific neighborhood. Understanding the dangerous hurdle happening in this section is absolutely crucial. See, traditional TV power boards supply 5 volts of electricity, but modern processors are incredibly fast and physically much smaller. What that means is their breakdown voltage drops significantly. They actually require 3.3 volts, or sometimes even less, just to operate safely. If you push that older 5 volts into a modern 3.3 volt system, you don't just get a little error message, you literally fry the processor instantly. So engineers are forced to create this kind of risky translation subsystem right on the board to step this power down safely. Moving on to section 2, LDO regulators, our voltage gatekeepers. All right, meet our first suspect. This is the component responsible for holding back that excess voltage we were just talking about. So let's define what this actually is. LDO stands for low dropout voltage. Now, technically, it's the differential voltage point where a circuit stops regulating to oppose input voltage declines. But, in simpler terms, it's basically a strict gatekeeper. It completely shuts down if the voltage drops below a specific critical threshold. This prevents any unstable power from reaching those highly sensitive digital components further down the line. To see how this builds, we can look at an operational amplifier, or op-amp for short, used as a comparator for LDO load regulation. Normally, the LDO is in there handling wildly fluctuating electrical loads. We're talking about rapidly stepping between 0 and 200 milliamps just to maintain absolute stability. It acts like a continuous monitor, keeping the intended output voltage perfectly steady, even when the TV's load conditions are varying drastically from moment to moment. But what happens when this gatekeeper breaks? Let's ground this engineering in reality for a second. The exact, super frustrating symptom of an LDO failure is a TV permanently trapped in standby mode. You press the power button, maybe that little red light flickers teasingly at you, but absolutely nothing else happens. This infuriating dead end is usually caused by an erroneous output voltage or maybe a failed internal pass resistor inside the LDO that effectively keeps the main board in a perpetual, unshakable state of sleep. No fun at all. Okay, on to section 3. Buck converters, stepping down power. Now, if the LDO is the gatekeeper, suspects 2 and 3 act as the absolute heavy lifters of the power board. Right on the main board, you've got U1, which is a 20-volt 3-amp buck converter, and right next to it, U2 is a 20-volt 2-amp step-down converter. These tiny little 8-pin chips take the high incoming voltage from the power supply and they buck it. That basically means they aggressively step it down to a much lower, usable supply for the rest of the board. But how do they do this without just burning up all that extra energy as massive amounts of heat? Well, they use a brilliant technique called pulse width modulation, or PWM. This means rapidly turning the current on and off to lower the average voltage, all without changing the maximum source voltage. Imagine a high-speed water valve pulsing on and off incredibly fast. The peak pressure of the water hitting the valve remains exactly the same, but the average pressure actually flowing through the pipe, that's greatly lowered. It's just a highly efficient way to manage power. Managing this pulsing current physically relies heavily on a few things: a transistor switch, a diode, and an inductor. They all work together to smooth out that rapid PWM pulsing into a nice, steady, clean output voltage. I mean, the rapid on and off switching would be totally chaotic on its own, so these components really act as an essential buffering system. Let's walk step by step through these ingenious mechanics. Step 1. The transistor turns on. The high voltage hits the inductor and the current begins to rise, storing energy. Step 2. The transistor turns off, but the current actually continues flowing, gracefully rerouted via the diode. And Step 3. The voltage is successfully lowered to a safe average for the processor. This microscopic cycle happens literally thousands of times a second. Converters can do this in what's called continuous mode, where the inductor never fully de-energizes, or discontinuous mode, where the energy drops to zero each cycle. When you look at the physical layout of the cascade transistors side by side with the internal schematic of U1, it really bridges the gap between abstract theory and physical reality. Engineers rely on this cascade topology because it allows them to generate multiple regulated low voltages using an absolute minimum number of switching devices. It's a super elegant design that saves precious space on the crowded main board and, of course, significantly cuts down on manufacturing costs. Up next, Section 4, the freewheeling diode defense. All this incredible switching speed requires a seriously robust defense mechanism to prevent the buck converters from, well, completely destroying themselves under pressure. Enter the freewheeling diode. It's a protective path allowing dangerous reverse current to safely dissipate when an inductive load abruptly interrupts power. See, when you abruptly stop current flowing into an inductor, it kind of panics. It reverses polarity and creates a massive, highly dangerous voltage spike as it desperately tries to maintain the current flow. So this diode acts as a critical safety vent, letting that reverse current harmlessly loop back around and dissipate into the circuit. So what does it look like when this heavy lifting system fails? Well, if a freewheeling diode blows out, the cascade switching transistors get hit immediately with that massive voltage spike. They take catastrophic damage. For you sitting on the couch at home, it results in a classic, pretty heartbreaking symptom. The TV turns on, looks like it's going to work for a split second, and then bam, it immediately shuts down to protect itself from further fiery destruction. And finally, Section 5, DDR termination, stopping data echoes. Now we're moving away from pure electrical power to our final suspect, which deals entirely with data power. High-speed RAM requires an endpoint shock absorber to stop signal reverberations. It's kind of like soundproofing an entirely empty room. When the TV's processor fetches data, that data travels down a transmission line. If it hits the physical end of that line without being properly absorbed, the signal echoes and reflects backwards, literally deafening the processor with overlapping electronic noise. The DDR terminator chip provides that essential end-of-chain absorption voltage, usually sitting right around 1.25 volts, just to catch and neutralize those data echoes. Recognizing a failure to terminate these data echoes is super important. When the DDR terminator chip shorts out, you get unwanted data skipping and massive signal interference. The TV's core processor just gets entirely confused by the noise and gets stuck in a desperate reset loop. And this results in probably the most mysterious symptom of all: random intermittent TV shutdowns. Your television will just turn off by itself at completely unpredictable times. You might literally be wondering if it's possessed, when really, it's just drowning in data echoes. This quote from our source material really sums it up perfectly. It says, engineers are constantly pushing the design envelope to meet the demand of larger screen LCD TVs with higher picture quality and loads of super data processing at super high speeds. Honestly, when you see all these interconnected systems, the LDOs, the buck converters, the DDR terminators, you really just have to respect the incredible, invisible engineering gymnastics required simply to turn on a modern screen and display a picture. So next time you press the power button and your screen lights up, will you think about the high-stakes, microscopic power struggle going on inside? The pulsing converters and the voltage gatekeepers, all working perfectly together? It truly is a modern marvel. Keep wondering, keep learning, and I'll catch you on the next explainer.